We have example problem number 65, found on page 96, chapter 5 on gravity. This question reads, what is the gravitational force between two 20-kilogram iron balls separated by a distance of 0.5 meters? How does this compare with the weight of either ball? So what they're asking us to find is the force due to gravity on the iron bars, the balls, and how that force due to gravity on each of them compares to their weight. Like what is that fraction? That's a good way of assessing it. What is the fraction? What is the ratio between the two? Given, well, each mass is 20 kilograms. Their distance is half a meter, and we know G is the gravitational constant, 6.67 times 10 to the negative 11th newtons kilogram squared per meter squared. So, equations. EQ, it's Newton's law of gravity. Right? So we plug our values in. So we solve the force due to gravity on these objects is G times M times M over R squared. So these are the same M's, so G times M squared over R squared. 6.67 times 10 to the negative 11 newtons. It's meters squared per kilogram squared times 20 kilograms squared divided by 0.5 meters squared. And that comes out to 1.067 times 10 to the negative 7th newtons. That's the force due to gravity they exert on each other. Okay? So that's this value. Now, how does that compare to their weight? Well, their weight is M times G. Okay, so that's 196 newtons. So, I guess one way we could do it, we could find the opposite. We could find how many times greater is the weight than the force due to gravity. If we flip it, it might be better. How much stronger, by what factor is the weight stronger than the force due to gravity they have on each other? Let's find the ratio of the weight to the force due to gravity that they exert on each other. So that would be 196 newtons divided by 1.067 times 10 to the negative 7th newtons. And that's going to equal, it's going to be a very large number, 196 divided by 1.067. Wow. Yep, it's 1.8 times 10 to the 9. Right? So it's almost 2 times 10 to the 9 times greater. So you can see that the force due to gravity that they exert on each other is significantly smaller than the force due to gravity that the Earth exerts on the object. So that just shows you how much more powerful Earth's gravitational force is on objects compared to the gravitational force that other objects exert on each other. Right? It's almost negligible, right? It's small compared to the force due to gravity. Why? Well, because the force due to gravity, the Earth is so massive. That's why it's so big, right? Because it's so massive. The distance between these balls and Earth's center of mass is the radius of the Earth, which is much larger than the distance between the two balls. But the mass of the two balls are so small compared to the Earth that the force due to gravity is is still significantly smaller between the two balls relative to the force of gravity of the Earth on the balls. So yes, so this is the ratio. So the force through gravity on the ball is many, many, many times greater. Times 10 to the 9, that's what, a billion? It's like 1.8 billion times greater than the force through gravity they exert on each other.